we will discuss velocities and acceleration. I'll start with something simple. I have a motion of an object along a straight line. We call that one-dimensional motion. And I'll tell you that the object is here at time t1. At time t2 it's here. At time t3 it's there. Time t4 it's here. And at time t5 it's back where it was at t1. And here you see the positions in x where it is located at that moment in time. I will define this to be the increasing value of x. It's my free choice, but I've chosen this now. Now we will introduce what we call the average velocity. I put a bar over it, that stands for average, between time t1 and time t2. That we define in physics at x as time t2 minus x at time t1 divided by t2 minus t1. That is our definition. In our case, because of the way that I defined the increasing value of x, this is larger than 0. However, if I take the average velocity between t1 and t5, that would be 0 because they are at the same position. So the upstairs is 0. If I had chosen t4 and t2, average velocity between time t2 and t4, you would have seen that that is negative because the upstairs is negative. Notice that I haven't told you where I choose my 0 on my x-axis. It's completely unimportant for the average velocity. It makes no difference. However, if I had chosen this to be the direction of increasing x, then, of course, the signs would flip. Then this would have been negative, and this would have been positive. So the direction that you are free to choose determines the signs. The location where you put your 0 is not important, but signs in physics do matter. Signs are important. Whether you owe me money or I owe you money, the difference is only a minus sign. But I think it's important for you. Now I will give you not only the positions as I did here on the x-axis at discrete moments in time, but I'm going to tell you exactly where the object is at any moment in time. Here you see an xt diagram. So you see that at t1, the object is at position xt1. This is the road of the object. This is the straight line where it's moving. It starts here, and it goes to this position. It goes to this one. It comes back to t4, and it comes back here. I will tell you now every moment in time in between. There it goes. Voila. This is now information that is way more. You have the information at any moment in time. Notice that I now did choose x equals 0. I chose it somewhere here. But I could have chosen it at any other point. For whatever follows, you will see that it makes no difference. So I have chosen a 0 point so that I can make a graph. And now we will look at the average velocity in a somewhat different way. Say I choose my time t2 and t3. I draw here now this line. And this angle I call alpha. And this part here I call delta x. And this here is delta t. And so you could write now, if you're careful about your sign convention, you could write down now that the average velocity equals delta x divided by delta t. But be careful, if the angle is positive, I call this a positive angle, then the average velocity is positive. But if I have a negative angle, then the average velocity would be negative. For instance, between t4 and t5, if I draw this line, then this angle here is negative, And so the average velocity between t4 and t5 is now negative. Again, if I had changed the 0 point, you would have found the same values for the average velocity. The only difference would have been the position of the curve in that plot. There is a very big difference in physics between speed and velocity. The average velocity between time t1 and t5 is 0, but the average speed is not. The average speed is defined as the distance traveled divided by the time that it takes to travel that distance. Now, what is the distance that the object traveled between time t1 and time t5? Well, the object started at a position here on this x-axis, and then it went up, reached the highest point here. So I'll make a drawing for you here. Reached the highest point here, then it went down, and then when it went here, it went up again, and it comes down again, and it's back. And in order to find the average speed, you would now have to know exactly what this distance is, add up this distance, add up this distance, and this distance. And if that distance altogether were, for instance, 300 meters, and if the time between t1 and t5 were 3 seconds, then the average speed would be 300 meters divided by 3 seconds. That would be 100 meters per second. So the average speed would be 100 meters per second, yet the average velocity would be 0. If you look at the location t3 and t2, and I bring t3 closer and closer to t2, then this angle of alpha will increase. And I can go to the extreme that I bring t3 almost right at t2. The angle of alpha will then be tangential to this point. This will then be my angle of alpha. And now you will understand how we define the instantaneous velocity at time t, which is different from an average velocity between two time intervals. The instantaneous velocity, v, and I pick a random time t, equals the limiting case for x measured at time t plus delta t, minus x measured at time t, divided by delta t, and I do that for delta t goes to 0. So think of this as being t3 and this as t2. I bring t3 closer and closer and closer to t2, and the time between them then goes to 0. And this is something that you undoubtedly recognize. That's the first derivative of the position versus time. And now comes an equation, which is one of the very few that I want you to remember. In 801, v equals dx dt. This is one that you must remember not only in 801, but for the rest of your time at MIT. And this could be larger than 0, this could be 0, and this could be smaller than 0. If the angle of alpha, the tangential, is positive, then it is a positive value. If it is negative, however, when you hear, then it is a negative velocity. And if the angle of alpha is 0, then the velocity is 0. So if we now look at this plot, we can search for the times that the velocity is 0. So you have to look for the derivative being 0. That means the angle alpha being 0. Clearly here, the velocity is 0. Right here at this turning point, that means when the object is here, it is 0. When the object is here, it is again 0 at this moment in time. Again, the angle is 0. And it is again 0 here. So those are the times that the velocity is 0. What are the times that the velocity is positive? Well, it's positive here. Velocity is positive here. Still positive, positive becomes negative. Negative, positive, 0, negative. So that's the definition of the instantaneous velocity.